Okay, so in this video, we're going to take a look at one last example of finding an inverse Laplace transform. And then we have just about all of the tools that we're going to need to actually apply this to solving differential equations. You might be wondering, where are the differential equations today? Today we're focusing on developing some of the mechanics that we're going to need working with Laplace transforms first, and then we can see how we can apply these methods to solving a differential equation. So trust me, we will get back to differential equations. Okay, so we want to find the inverse Laplace transform of f of s, which is minus 5s minus 36 all over s plus 2 times s squared plus 9. Yowza. Okay, so the bottom is factored. So whenever we can factor it, the first thing that you should try and do before you try and do any sort of completing the square is try and factor the denominator and then use partial fraction decomposition on the denominator. So we're going to take this denominator, s plus 2, and write it as a sum of something that looks like a over s plus 2 plus, and then the other factor is s squared plus 9. Okay, and notice that this factor actually, we can't factor it any further. That's factored as far as it can go. And so we have a quadratic on the bottom. So when we do this process of partial fraction decomposition, you always put on top in the numerator of each of those factors an expression which is 1 degree less. So we've been mainly dealing with, when we saw these earlier in the semester, each of the factors was linear, so we just had a constant up top. But in this case, we have a quadratic factor that can't be broken up anymore. So then we're going to put an arbitrary linear thing on top over here. And then you can match things up and try and figure out what are the values that we need for A, B, and C, so that when we add this fraction together, we get minus 5s minus 36 up top. So I will kind of skip that process because it's kind of tedious, but I will tell you that when you do this, you should check it, and what you would get is that A is equal to minus 2, B is equal to positive 2, and C is equal to minus 9. So what that tells us is that this function that we started with, f of s, we can actually break that up and write it as minus 2 over s plus 2 plus 2s minus 9 all over s squared plus 9. And then we look at our table of integrals, okay, which I've taken the relevant ones and pasted them over here. And so for example, this one over here is very much so an exponential looking thing. So when we take the inverse Laplace transform of this one, the minus 2 can be brought out front, and then we take the inverse Laplace transform of s plus 2, which is going to give us e to the minus 2t, right? Because the a value here is minus 2. And then we've got an s squared plus 9 over 2s minus 9. So here we have things that look more like exponential times sine or cosine, but we have a little bit more work to do with this one. So if I take this and we can break it up, haven't done Laplace transform of anything yet, but I can write this as 2 times s over s squared plus 9. So that takes care of the 2s. And then for the other part, we're going to have some constant up top, right? Because we have that minus 9 up top over there. But if I want to use something that seems to look like e to the at sine of bt, because that's the one that has the constant up top, in this case, our value for b is 3. So I'd want to have a 3 up here, and then I could use that Laplace transform, but we had a minus 9 over here. So in order to fix that, I must have a multiple of 3 in front of that one over there. And so now we can apply the inverse Laplace transform to each of those. So I'm going to get 2, and the inverse Laplace transform of this one matches up with the cosine, where we have a is equal to 0 in this case, and b is equal to 3. I guess I don't need that exponential term there at all. But this would give us cosine of 3t. And then for the other piece, we've got this minus 3, and then what we have is e to the 0t times the sine of 3t. So altogether, our inverse Laplace transform of this function f that we started with would be minus 2 e to the minus 2t plus 2 cosine of 3t minus 3 sine of 3t. So definitely get started practicing on doing Laplace transforms using the table of Laplace transforms and the properties to find inverse Laplace transforms. There are some problems on homework that you can use to start practicing these concepts, and I would encourage you to get some practice on this now before moving on to the next set of notes, which is going to assume you've gotten some practice with these types of exercises already.